Hi, welcome to our next episode. So today we will show you how to make a regulated power supply. And to do that, we will first design a bridge rectifier to make a raw DC out of it, and then we will do the rest of the circuit with the components needed, and after that we will show you how the whole circuit works.
So let's start with the breadboard. This, as you can see, this is the breadboard, and now we will take a transformer. So a 12 volt transformer. This is a transformer which produces a 12 volt secondary AC from a 220 volt AC line. So we have connected the AC line to the main, and we will take two output from a common and one side of a 12 volt. So next we need 4 diodes, normal diodes. 4 normal diodes, which is IN7004. This will work for a bridge rectifier, and later on we need a capacitor. We will take a 1000 microfarad capacitor, which is quite big, and it is of 25 volts, so that it can the output does not burn the capacitor. Okay, so this is the bridge rectifier circuit. As you can see, this is the AC main part, and from that this is the center tap, and it is the one terminal from where we will start our circuit of the bridge. Here are the diodes, 4 diodes. We have named them D1, D2, D3 and D4. This is a diagram of a diode where it shows the positive side, P side, and this is the N side. So you can see that D1, D2 has a connection of the N side of D1, and P side of D2 is connected to one end of the output, secondary output of the transformer, and the second end is connected to the N part of D4 and P part of D3. And then we will take the output of this bridge from the connection of both P side of D1 and D4, and from the N sides of D2 and D3. So this output then are fed to a capacitor to get the unregulated power supply part. So that's how we will make the bridge circuit. So here you can see we have made the bridge circuit. As you can see the circuit diagram also above. So like the diagram, we have done it that D1 and then D2, D3 and D4. Here one thing you have to notice that the diode you can manage how the P side and N side of a diode can you can check it from a gray band is the N side of the diode, and the black side is the P side of a diode. So this is the bridge circuit we have made. Now we will set up the connections with the transformer. So as you can see, we have connected the bridge D1 D2 junction with one of the secondary port and the D3 D4 junction with the another port. So this is the complete bridge circuit, and then we will take the output from the two other points, that is D2 D3 connection and D1 D4 connection, and then we will put a capacitor of 1000 microfarad to get a raw DC. So now we will measure first the DC output of the bridge. So if we put a DC multimeter on the D1 D2 D3 connection and D1 D4 connection, then we get approximately 12 volt, 12.3 volt of DC. So this is a quite good DC, but we will make it better by putting a capacitor filter, and that capacitor filter will make the amplitude enhanced by some value. As you can see, the capacitor, the positive part of the capacitor is connected with the D2 D3 junction, and the negative part of the capacitor is connected with the D1 D4 junction. And let's take the measurement of the raw DC output from the capacitor. Now if we put a multimeter, then you can immediately see the voltage is enhanced to 17.68 volt, which is quite high from the original value of the bridge output. So we will take this unregulated part as the input of our regulated power supply now. So this is the regulated power supply circuit. From here, this is the unregulated part from where we will take the input of the circuit, and this is the transistor Q1, which we will take 2N3055, and this is the Q2 transistor, which is CL100, and this is a 5 volt Zener diode. Here, this is the resistance RS, which is connected to the Zener circuit, and these are the R1 and R2 resistances, which are actually made by three resistances: R1 prime, R2 prime, and a potentiometer, whatever we call it. So here we can actually measure the output of the circuit, and there we will measure the current, load current, by a multimeter, and it is the load resistance, and here we will connect a voltage to see the voltage of the output, a voltmeter. This is the whole design procedure of the regulated power supply, and we will show how a 10 volt regulated power supply can be designed. Okay, let's start with the scratch. We want to make a output voltage 10 volt with maximum load resistance 100 milliampere. we choose a reference voltage, that is the Zener voltage of 5 volt and the Zener current as 5 milliampere. So the calculation of RS comes from this Vout minus VR by IS, and this comes out to be 1 kilo ohm. Here we have made the measurement of HFE from both the transistors. First 2N3055, which has a beta 53, and of CL100 the beta is 242. Here we have chosen IC2 and IE2 to be almost same as 5 milliampere. So IB2 comes out from this formula, and this is of 20.66 microampere. Now we can calculate the V2, which is VR plus VE2. This is 5.7 volt, and from that you can calculate the R2, which comes out to be more or less 1.14 kilo ohm. And we have chosen I1 as 5 milliampere. R1 comes out from this formula V out minus V2 by I1, and this comes 860 ohm. IB max comes from the formula IL max plus I1 plus IS by the beta 1, and from the calculation we get 2.07 milliamp. So total I is IB1 max plus IC2, which comes out to be 7.07 milliamp, and the R3 comes out to be VI max minus VBE1 plus V out by the total I. Here VI max, as we have shown that from the bridge output we get from the capacitor terminal 17.68 volt, and VBE1 is 0.7 volt, V out is the desired 10 volt, and the I, as we get 7.07 milliamp. So R3 comes out to be 987 ohm, and the RL minimum comes from the calculation V out by IL max, and this is a 100 ohm resistance. Now we have a practical choice of the resistance, and from the choice we took the closest resistances we get, and RS we get 1.06K, R3 as 1.05K, R1 plus R2 as we have divided at R1 prime as 338 ohm, a 1K pot, and R2 prime as 713 ohm, and RL mean as 102 ohm. So this is the whole design procedure and the resistances we will use in our circuit. So as you can see, this is the whole circuit diagram, and we have mentioned the values. The unregulated power supply, the VI max is 17.68 volt, and the Q1 is taken as 2N3055, the power transistor, which has a beta HFE1 which is 53, and Q2 is taken as CL100 which has the beta HFE2 as 242 volt. The Zener has a voltage of 5 volt. R3 is 1.05 kilo ohm. RS as 1.06 kilo ohm. R1 prime is 338 ohm. Pot of 1K, and R2 prime as 713 ohm. And RL minimum is 102 ohm, and we have taken along with a 10K pot to make the whole design. So we will use these things to design the circuit. So as you can see, this is the whole circuit we have designed. So we have taken the input of the circuit as shown in the diagram previously from the positive side of the capacitor and the negative side of the capacitor. Here this is the R3 chosen as 1.05 kilo ohm, and this is the Q1 transistor 2N3055, which is the power transistor. This is the collector, and this is the base, and this is the emitter terminal of this, and this is the Q2 transistor, which is CL100, and this is the emitter junction, and this base junction of Q1 is connected to the collector of the Q2, and the base of CL100 is connected to the middle point of the potentiometer, and this is the RS taken as 1.06 kilo ohm, and this is the 5 volt Zener, which is connected from the emitter and to the ground, and this is the R1 prime, which is taken as 338 ohm. This is the 1 kilo pot, and this is the R2 prime, which is 713 ohm, and this is the RL minimum, which is 102 ohm, and we have taken a 1 kilo pot with this to regulate the voltage, and this is the milliammeter connected in series and the voltmeter in parallel with the RL to calculate the voltage output and the current output. Now we will power the circuit, and then we will show how it works. Here, as you can see, we have powered the circuit, and we adjusted the pot of P of R1, R2, and from that we can actually get the desired value of the output. Here we have chosen as 10 volts, so we will put it as 10 volts. So this is almost 10 volt, and now you can see as we have disconnected the load, one part is now disconnected, so the IL is 0. Now we will put the connection here and we will see how it works. So this is the minimum value of the current at RL min, and this is the output voltage 9.91 is almost 10 volt. And now we will see how it works, the load regulation works. As we will increase the value of the potentiometer, the current increases, and it almost remains constant but decrease slightly. So as you can see, we are going higher with higher and higher value, and as we go farther we reach a maximum of 78 milliamp at voltage output 9.27 or 26 volt, which is a quite good regulated power supply we have made. So I hope this helps to design you a regulated power supply of your desired voltage. So here you can see how the voltage regulation works. So from start, this is for the RL minimum, this is almost 8 milliampere and the voltage is 9.88 volt. And now as we increase the load, as you can see, the current is increasing. At the same time, simultaneously the voltage tends to decrease, and as we go farther and farther, it goes to 78.3 milliampere when it decreases to 9.28 volt. So this is a regulated power supply, as it works and it regulates the voltage. I think it will help you to design a regulated power supply of your desired voltage, output voltage. Thanks a lot. So here we show how to make a line regulation for this regulated power supply. To make this, from the output of the unregulated power supply, we make a voltage divider by this potentiometer, and the last two ends are connected with the positive terminal of the capacitor and the negative terminal of the capacitor, and from the middle terminal, the input of the whole regulated power supply is now taken. So this makes a divider, voltage divider, from which we can vary the input voltage, just like this. So as you can see, that as we turn the pot, it changes the input voltage. And here, for line regulation, we first fixed a load current value. Let's say we set it at 20 volt, 20 milliampere, sorry. Now we will try to show how the output of the regulated power supply changes with the input of this RPS. So as we now try to change the input voltage, you can see the output also changes. So that's how you can actually maintain the line regulation for this RPS.